Welcome to another episode of At the Workbench at 4111 Spyglass. Last week, this setup was a disaster. Packets dropped, bytes corrupted. Sometimes only one packet out of 100 made it through. At other times, I'd see fragments of the message, missing characters, random substitutions or extra garbage. And today, you may ask, it works flawlessly. So what happened? Let's walk through the week where everything broke and how it finally made sense and everything came together. What are we trying to achieve? We're building a deterministic USB radio USB pipeline using the CC1101 chip operating at 433 MHz. Why? Because this setup forms the backbone of a telemetry link from an autonomous vehicle or satellite down to a ground station and a command uplink in the other direction. On the vehicle, we'll eventually replace the USB with a generic stream, but this bench setup lets us iron out the real problems first. What are the requirements, you may wonder? Variable packet lengths, robust state machines, reliable communication. It sounds simple in theory, but radio links are never that simple. Last week, we had many failures and setbacks. We didn't capture every failure on camera, and honestly, that's fine with me. The important part is understanding what the failures meant. Let me list them briefly. Poor connectors, antenna orientation and distance, chip power on reset, registers, their modes and flags, generating and catching interrupts, critical sections inside the state machines, their implementation and timing, timeouts, buffer overflows and underflows. Let's start with the most embarrassing failure, the DuPont connectors. I decided to crimp the cables myself using the connectors from the kit. The female sockets were too tight. The male header pins just touched them instead of seating properly inside. The male pins were flimsy. Even tiny movements broke contacts on the breadboard. And of course, radio modules absolutely hate intermittent ground or power. I had just enough pre-crimped wires with proper male-female ends. Once I switched to those, everything seated cleanly. Lesson learned, buy connectors from a reputable brand, not the cheapest Amazon listing. While testing the transmitter last week, I used an SDR to verify the signal. On the SDR waterfall, I saw these strange lenticular patterns, beautiful but unexpected and clearly wrong. I should have investigated them. Because the very next day, with both transmitter and receiver running, only a handful of packets made it through. Now I was debugging two systems at once. The root cause was the same in both cases. When the antennas were too close or perfectly aligned, the receiver saturated. The SDR's automatic gain control overcorrected, creating that oscillating pattern. The CC1101 saw thousands of spurious events, distorted preambles, and drowned out real packets. As a result, the receiver discarded most packages it picked up from the transmitter. The fix is simple enough. Move transmitter and receiver apart, or at least reduce their gains. The CC1101 needs a few SPI ticks after chip select goes low before it's ready, especially after a reset or when waking up. If you don't give it that, the first exchange fails and one reads garbage. I was clever enough to read both part num and version first, but I also checked their values and aborted when they weren't correct. Sometimes they were correct just by chance, which confused me for far too long. The fix is simple. Send some dummy bytes first. For example, read the part num register, ignore the result, and move on. Mark state, RX bytes, TX bytes. All these registers require the burst flag. Without it, you're reading the wrong register. The CC1101 overloads the burst flag. It's used for multiplied config, read, and writes. It's ignored for command strobes. It must be used for status registers. It can be used for FIFO access. My helper functions blurred these distinctions, and I kept mixing them up. Even if you get it right in one place, a few lines down, it may get mixed up again. The fix was proper software engineering. Define separate enums for config registers, status registers, strobes, and buffers. Build helper functions that only accept the right enum. Once that was in place, the confusion disappeared and register access worked correctly. We set the receiver interrupt to a falling edge. We start with event type 7, which asserts when a package with the correct CRC is received. That fired too early and triggered the handler at the wrong time. We switched to event type 6, which asserts on synchronization and deasserts at the end of the packet. That was more reliable, but also triggered much more often, which required the state machine to filter events and data. Between assert and deassert, rising and falling interrupts, and using the same configuration for transmit and receive, it was easy to get lost. For now, we use event type 6 with falling edges. We may revisit event type 7 with rising edges later because it should high-grade events and simplify processing. The CC1101 datasheet is clear. Only read the RX FIFO when the bytes in FIFO are larger than the packet length plus 3. Otherwise, RSSI and LQI aren't there yet. My first implementation was experimental and full of ad hoc checks. The state machine looked simple, but became unreadable fast. The result? We were reading random FIFO data, underflows because of data that hadn't arrived yet, and so on. The fix? To refactor the state machine into smaller, more focused pieces. Reduce coupling between state machine and handlers, make the logic obvious, clearly show what is going on. In short, follow clean code principles. RF packets can be up to 61 bytes long. To avoid overflows, we set the USB buffer to 41 and trigger transmit when it filled. And then we wonder why data was missing or wrapped around. Same root cause as always, magic numbers. The fix? Define explicit constant and remove the magic numbers from the code. In short, clean code principles once more. Our USB buffer was 41 bytes long, but the print function thought it had 128 bytes. Of course it wrote past the end. Of course USB transmitted garbage, for example lines glued together and so on. Once again, the problem was magic numbers. The fix? Define constants, use these constants everywhere. Do I need to say it again? Clean code principles. Once all the layers aligned, hardware, RF, SPI, CC1101 quirks, USB timing, buffer sizes, the system became completely deterministic. RF debugging is physical. It includes hardware and software. Embedded debugging is systemic. Every bug is multi-layer until proven otherwise. And clean code really matters. Software development practices really matter. Skipping test-driven development because the examples are small, it keeps biting me. Next time on At the Workbench, we will combine receive and transmit on the same node with an arbiter to grant hardware access. We will perform manual gain experiments and range tests. Thanks for watching this episode of At the Workbench at 4111 Spyglass. See you next week.